Fractals are fundamentally a complex and irregular shape, with this complexity still present at smaller scales. They are often described as possessing the property of self-similarity, meaning that the component parts resemble the whole, resulting in the same shape despite the scale. The concept of fractals was first introduced by Felix Horsdorf in 1918. However, self-similar geometric patterns can be found naturally, such as in tidal channels, ferns, and pine cones. The term fractal was coined by Benoit Mandelbrot in 1975. Mandelbrot identified that fractals are a powerful mathematical tool that can be applied in modeling a variety of phenomena, from physical objects to the behavior of the stock market. Fractals change the way we can view the world around us, through an abstract take on geometry and dimension. Dimension can be considered as how much space a shape fills, and is defined by a scaling dimension relationship. This relationship says that the copies required of a shape equals the scale factor to the power of its dimension. Take a line for example. If you want to scale it up by a factor of 2, and we know it has a dimension of 1, then this relationship says that you will need 2 copies of the original line in order to do so, as expected. Now if we consider a square that we want to scale up by a factor of 3, then we can see that 3 to the power of its dimension, which is 2, will tell us we need 9 copies of the original. As can be seen, the same relationship holds for volumes. Now let us consider a fractal such as the Sierpinski triangle, which is just an equilateral triangle subdivided repeatedly into smaller triangles. It can be seen that the shape doesn't actually completely fill the 2D plane, and hence we can intuitively conclude that it will have a dimension slightly less than 2. Rearranging the previous formula gives us that dimension equals log of copies divided by log of the scaling factors. Say we want to scale a Sierpinski triangle up by a factor of 2, we can see that we will require 3 copies of the original shape. Log 3 over log 2 gives us a dimension of approximately 1.6, similar to what we expected. The concept of fractals and the new take on the idea of dimensions has been applied in a vast range of areas of study. The study of fractals behavior allows for the prediction of patterns in systems which on the surface seem unpredictable. Fractal analysis allows for the determination of when the features of complex systems are altered, as this influences their complexity, which is in essence what their dimensions represent. Areas where fractal statistics have been applied include cloud formation, weather systems, and animal migration patterns. Fractals have been applied practically well before they are defined, with the South American Incas constructing bridge cables made using grass weaving techniques, which represent fractals, with similar techniques still being used today in steel cables. Fractal patterns based off the ones found in blood vessels are being etched into silicon chips, allowing for an effective uniform distribution of cooling fluid across the chip. On a larger scale, scientists are investigating the possibility of the structure of the universe being fractal rather than uniform as previously thought. If this is proven to be true, all models including the Big Bang will have to be adapted. It has been discovered that the galaxy correlations are fractal, with their structures being highly irregular and self-similar. This is just the tip of the iceberg of new developments that fractals have enabled, with plenty more likely to come in the future.